So, what is your idea of the thick present?
involving time. Now, the thick present is an idea of some philosophers, I don't remember who right now, that time has an extension, that so that there can be two events which are at the same time, but one is to the future of the other, or the other way around. So, as a technical idea, it's clear when it's it's to be subtle, though. Does it violate relativity? And I think it challenges relativity.
What's the difference between contradicting relativity and challenging it?
Understanding something and not quite understanding it yet.
So, there's something that you have invented called doubly special relativistic theory.
With some friends, yes.
Yeah. What is that, and does that violate Lorentz?
It extends Lorentz invariance. The idea of doubly special relativity is that, well, let's go back to special relativity. In special relativity, we have one scale, one velocity, which is invariant. So when we travel, if we're traveling, you're going that way, I'm going this way. We have a relativity, Galilean relativity, whereby our length and time measurements change relative to each other. But in doubly special relativity, we impose the constraint that not only is the speed of light fixed under those transformations between frames, but so is an energy. So that if we measure a energy of some particle, we can transfer between your measurements and mine, and the transformation will be more complicated in such a way that there are two length scales, or one velocity and one energy, which remain invariant.
So, is another way of saying that there's a universal cosmic speed limit, which all observers agree on, but then also a universal cosmic limit to the length? So the Planck length is somehow also fundamental?
Yes, although I'm trying to keep h bar in the game. So I'm trying to, I want to pick whether it's an energy that's invariant or a length that's invariant. I don't want to assume that h bar equals 1. And what you decide is that what's invariant is the ratio of what we usually call the Planck energy to what we usually call the Planck length.
Why is it that you don't want to set h bar to equal 1? Is there something that you feel like is lost?
Yes, because if we want to have a theory which explains h bar, it can't be one in which h bar equals 1.
Uh-huh. So what led you and your collaborators to develop this?
Sabine Hossenfelder, to be short. We had a previous theory which was doubly special relativity, and we didn't understand it completely. And Sabine saw that there would have to be non-locality in some field theory if that theory was going to encompass doubly special relativity. And so we then, and this was 4 of us, we were working together a couple of times a year at Linear, and we realized more or less simultaneously that the way to answer Sabine was to let simultaneity be relative and also let locality be relative. So whether some interaction took place locally or non-locally was dependent on whether you were close to the system being observed or far from it.
Mm-hmm. So what did Sabine say to the concept that locality itself is a relative concept?
She didn't like it, and we continued to have disagreements, and I think she continues to disagree with us.
And her disagreements are
that you can have a theory. Now we call the theory, with these amendments, we call it relative locality, because that's a more precise description.
Okay. Speaking of what's relative, there's something called A and B series of time.
Yes, I never remember which is which, but in one of them, the one says that relative time position. So I talk about your yesterday, or my future, or the dog's past, and those are relative to the dog at some moment. The past of the dog is not the same as the future at another time. And this is one view that that's okay. And the other view is the view that really there is no time, so that there is only, I think I'm saying it backwards. In the one view, let's call it the A view, although I'm not sure that it is what it's.
Sure.
You can be an observer to the future of another observer. And we allow that is, we allow ourselves in the theory to discuss relative time as realistic, real things, but relative to an observer, if that makes sense.
And is this related to your thick time or no?
It needs thick time to make it consistent.
Have you heard of Nicholas Gissens or Nicholas Gissens?
Oh, sure.
Well, what is his concept of thick time, and is it different?
I don't think so, but I haven't studied it.
Okay. So explain to me why thick time needs, or why A or the B series needs thick time.
Can we come back to that?
Sure. Something that the viewers may notice by now, and I've already mentioned it in the introduction, is the movement. And you mentioned that you don't want to hide any of this.
Well, it would be hard to.
Yeah. So can you explain?
What you're seeing is an overcompensation for Parkinson coming from taking a bit too much dopamine, which is, in the context of being interviewed, a good thing to do.
Why?
Because the other setting, it's a very quick transition. And I think it is a phase transition. By the way, I'm doing some work on the brain and the regions of the brain which are relevant. It seems to be that there is a phase where things seize up in the control of the brain.
Yeah.
And a phase where things go uncontrollably nuts.
Okay.
And you want to be in a kind of critical state between them.
Yes.
And that's what the dopamine allows you to reach.
Yeah. And so right now you're in the critical phase, or you're pushed off to one of those directions?
I'm way overcompensated.
Oh, but does that mean that with time it will get better, or
Yes.
with time it gets okay? With time throughout this day, I mean.
It's coming right up.
Oh, okay.
And you'll see it happen because the critical phase, as in most physical systems that have a critical phase, is a cause of critical vibrations. So you'll see, I'm making it happen, but you'll see half an hour from now my things going critical, with critical scaling, and then it'll be over.
Does it just affect your physical body, or does
It affects everything.
Okay, how does your mental state or your state of consciousness affect it?
It makes me, I don't have much of an executive function when it's on strong.
Uh-huh.
So that's the worst thing. If I can overreact.
Yeah. So why don't you talk about how you studying physics, well, it's more like researching physics has been impacted. Your collaborations even.
It's more irregular. That is, working with my collaborators, I'm on more, and we use the words on and off. So, but I don't know. You have to ask them. Although I don't know if I want to know the answer. I'm glad to have still collaborated.
When we talked a couple of years ago on the phone briefly. I don't know if you recall, but I was asking if you had taken a look at geometric unity because I was going to be interviewing you at that time, and I was giving an overview of some of the questions. And you mentioned Eric is a dear friend.
Yes, he has to be. If he's not your dear friend, he's not going to be your friend.
Yeah. Okay, so can you please talk to that? And then also geometric unity.
Eric is, well, his strength as a researcher is certainly his commitment, and he's extremely smart, extremely quick, and he can go at something for years and years and years. And that's very important if you're trying to do original work in physics or anything else, I would think.
Is this quality of going forward on a single idea or a single theme for years rare?
Yes.
So it seems like for me, when I was reading your work, and by the way, you don't know this, but so my background's in filmmaking, like math and physics, and then I did a film.
Okay. What was the film?
Film is a dramedy, so comma dramedy, called I'm Okay. It's a heavily Toronto-based film.
Oh, so I may know people in it.
Yeah.
Because I know a lot of film people.
Yeah, and so when I was filming it, and I had the cinematographer in my car and the sound recordist in the car, we would be listening to your book.
Oh, wow.
Yeah, one or two of them during the filming of it. Anyhow, that was a fun experience because they would ask me, what's a Calabi-Yau manifold? They wouldn't pronounce it like that, but they would say, so what is that? And why does that have anything to do with background independence? And why does background independence matter? Why does gravity have anything to do with curvature? Curvature of what? Space? No, not curvature of space. Curvature of space-time, which is different than space. Anyhow, this interview itself, just meeting you, it's a dream. I would be listening to you in the car. I had no idea that I could ever not only see you in person, but shake your hand and speak to you like this. So thank you.
You're welcome. But that's extraordinary to me because I just live here. And I don't feel very well. The Parkinson's has a way of leveling things.
Mm-hmm.
I would say everything is now in question. Every interview, every talk every paper is a experience sort of on the edge.
Meaning that you don't.
I don't rest on reputation. I can't. But the work that I'm working on now is my favorite work. I'm very impressed with it, which is a funny thing to say, that you're impressed with your own work. But
if you enjoyed that clip, then the full podcast is out right now. You can click around here. Enjoy. Subscribe to Theories of Everything to get notified of upcoming podcasts, as there are new full-length podcasts every week on the topics of mathematics, physics, consciousness, free will, and AI.